Justin Miller, Oxnard College Physics here, and we are moving forward into what you may ask, moving into electric field flux. What did I just say? That's right, you heard it, electric field flux. So, electric field flux. Well, what do we want to do with this? We want to understand what the heck is flux. What the flux is going on? Anyways, so what do we got? What is flux? Well, flux is the amount of the electric field that goes through some area that is under consideration. So, flux we'll call phi sub E. This is electric field flux. Capital Phi sub E is the amount of an electric field that penetrates through some area of cross-section. Some cross-sectional area. So that's it. There it is. It's the amount of the electric field that penetrates through some cross-sectional area that's being considered. So there's some easy instances to understand flux, and then there's some more difficult, which we'll get into the more difficult as time goes on. Let's stick with something easy right now. So let us consider that this grid here is the area that I want to consider the electric field flux through. And we'll also consider that there's an electric field in this room, this is per se, for example, that is pointing uniformly towards me and has the same magnitude everywhere. So we've got a uniform, constant electric field pointing inward towards me. And I hold this sheet out like this, such that the plane of the sheet is completely perpendicular to the electric field. And I say, what is the flux, electric field flux through this sheet? And well, what that ends up being is the total electric field that is going through the sheet. What is that? Well, it's the electric field strength, in a sense, multiplied by the area over which that electric field is going through. So that is the flux. Well, what happens if I start rotating the sheet a little bit? What happens if I say go like this? And say, well, what now? Well, the amount of the electric field that goes through it is different than when it was like this. Why? Because there's less forward-facing area for the electric field to penetrate through. In essence, I have reduced the area through which the electric field can penetrate by undergoing this rotation here. So what happens when I go like this and say, well, how much of the electric field goes through it now? Well, the flux through this sheet, if the electric field is pointing towards me, is 0 now. If this sheet's plane is aligned with the electric field, because nothing's going through the area of it, everything's going through this way. There's no penetration through the area of cross-section. So there's something about the orientation of the area under consideration with respect to the electric field's direction that needs to be considered in incorporating the idea of flux. But really it's just how much and what is it going through. And what we do with this is take a nice simple case and say if the E hat field being considered is uniform, constant magnitude and direction, across the area being considered, and orientation of the area the same everywhere with respect to the direction of the electric field. The electric field flux is given by the capital phi sub E is, that's a bad E, capital phi sub E is equal to the dot product between the electric field vector and area vector. All right, so let's take a little bit of a look at this. This, again, is only if the electric field's orientation is the same everywhere with respect to the orientation of the area vector, and the electric field is uniform over that area, constant in magnitude. So, area vector, let's do this. A hat has some magnitude, which is the area, the scalar quantity area, and has a unit vector association that is normal to the plane of the area. So n hat is the unit vector, which is normal to the plane of the area. So if we're talking about an area that has the same orientation as the electric field everywhere, well, we'd have to be talking about a plane then, if the electric field is uniformly directed. So that would be something like this. What does the area vector look like with respect to this sheet here? Well, it has an area of the length times the width. And what about the direction of that area vector? Well, the direction is perpendicular to the plane, normal to it, which we could say is either outward this way, or we could say is inward this way. As long as it's perpendicular to it, we're good with this. Really, whether it's this way or this way is a matter of perspective. We're not going to get hung up on that too much at this point. It becomes important a little bit later, but that's going to be easy to deal with. So right now, all we got to deal with is, hey, it's either opposite directed with respect to the electric field, again, assuming the electric field is pointing towards me, or it's in the same direction as the electric field when the orientation of the paper is completely perpendicular with respect to the electric field. And then what happens? Well, we have that dot product, E hat dot A hat, really resolves into something, right? We have that is EA times the cosine of theta, where theta is the angle between E hat and N hat, where N hat again is the normal vector associated with the area vector of area under consideration. So there's this angle here. Well, again, if the electric field is pointing towards me and I hold the sheet such that it's pointing perpendicular to the electric field, we could say that theta is either going to be equal to 0 degrees or 180 degrees. What does that give us? Well, it gives us that this cosine of theta would either be 1 or negative 1 then. So what would we have? This is 1 or negative 1, and we'd have that the flux is either positive E times A or negative E times A, where E is the magnitude of the electric field, and A is the area that's under consideration, the area of the sheet in this case. Positive or negative, really that comes into, are you considering it coming in or going out? Not worried about that right now. Really, in this particular sort of case, we just treat it as positive and say that the area vector is in the same direction as the electric field. But that's mincing things a little bit. It's not that big of a deal. The big deal is that there's this angle right here. Well, what happens when I turn the sheet like this? What's the angle now? Well, it's 90 degrees with respect to the direction of the electric field. And what do we get out of that? What's the cosine of 90 degrees? Or 270, doesn't matter. What is it? Yeah, that's right, it's 0. What's the flux through the sheet if the plane of the area is parallel to the electric field? There is no flux, it's 0, that's right. And the cosine of 90 degrees is equal to 0, which says that the flux through it's 0 in that particular orientation. And then we have everything in between. As we rotate this, again, the forward-facing area for the electric field to penetrate through is reduced down to 0 when it's 90 degrees with respect to the direction of the electric field. Talking about the area vector there. So that's what we've got going on. We've got a nice planar area and a uniform electric field over that area. So that seems pretty easy, right? Just calculating flux. That's flux, that's it. What about the units of flux? Electric field flux. Well, that should be pretty easy to figure out, right? We've got ourselves SI units of phi sub E. We got electric field. What's the units of electric field? Newtons per coulomb. What's the electric field? Excuse me. What is the units of area? SI units meters squared. So what do we have? Newton meters squared per coulomb. There we go. Newtons per coulomb times meters squared. There's our unitization of electric field flux. So, again, for the uniform cases, everything's pretty simple. If E hat is not uniform and or the orientation of A hat varies with position regarding E hat, we must integrate. To determine the flux, the electric field flux. How are we going to do that? Well, that's going to be easy. We just have to add up the contributions of the electric field over the area and really only take into account the parallel component of the electric field with respect to the area vector over that area under consideration. Which, what does that amount to? We've got ourselves the electric field flux is then going to be equal to the integral over the area that's being considered of E hat dot dA hat. There it is. So what do you got to be careful of here? Well, number one, it's a dot product, and if we have variance between the direction of E hat and the elements dA hat, spatially, we have to have some way of describing that variance, which can be actually pretty difficult, or it could be easy. It just really depends. And then we can have E as a function of position itself over the area. That's great. But this is a vector operation here. We have to integrate over a vector operation. So you got to be really careful of something like this. And furthermore, this really kind of breaks into a double integral because you got dA, we could break it into dx dy or dr d theta, rd d theta. But anyways, we're not going to really deal with something on this complex of a level. This is an important notion and we're going to utilize it, but we're going to keep kind of specialized cases where we can integrate things pretty darn easily. But that is, in general, how we determine the electric field flux through some area. And again, think about this, right? What if we had some area that was like this? Here's our area that's being considered, has different directions everywhere. Even if we took a uniformly directed electric field that was even constant in magnitude and direction, what would we have to do? Well, we would have different normal vectors associated with the area vector at different locations. So I could say that the normal vector here, well, that looks like it's in line. So there's our little n hat. I should go ahead and write this be like our E hat. But then if we go over here, and again, we'd have to do it everywhere. This is just looking at a couple spots. If we go over here, well, the normal vector here is pointing like this. Put that, should just be that. Back over here, well, now it looks like that again. Over here, it looks kind of like this. Over here, over here, over here. The point is that the orientation of the electric field with respect to the area vector is different at different locations. And if we want to actually add up all of the contribution, we've got to take all of that variance into consideration, which can make this difficult. It really just depends on the contour, though. And this would be, again, with the case that the electric field is uniform. If the electric field is not uniform, we could have an electric field that's like from a point charge, radially outward, varies with position in terms of the distance away and varies with direction as well. And then have some contour like this. What do you get then? You get something that's a lot more complex. But hey, that's it. That's what we want to kind of look at and appreciate. So, electric field flux. What's flux good for? Well, it's good for something that we're going to talk about right now, other than just, hey, I can calculate the electric field flux. All right, so let us go ahead and now venture into the realms of Gauss's law. That's right, Gauss. Maybe you've heard of Gauss, Gaussian distributions in statistics, stuff like that. Or maybe you've just heard of Mr. Gauss himself in terms of Gauss's law. But what I want to do is, hey, utilize Mr. Gauss's law and see what it's all about and see how it correlates with electric field flux and what can be extracted out of Gauss's law. So, Gauss's law. All right, so Gauss was a pretty smart guy that came up with a law that ultimately correlates electric field flux through a closed surface and the charge that's enclosed by that surface. Whew. Gauss's law says the net electric field flux through a closed surface is proportional to the amount of charge enclosed by that surface. Now change charge enclosed by that surface. Say, well, that sounds pretty cool. Electric field flux correlates with charge enclosed by a surface. So what do you mean by a closed surface? Closed surface, well, would have to be a surface that wraps back around on itself. We can't be talking just about a sheet anymore. That sheet would have to wrap back around and become maybe a cylinder. Then we'd have to close off the tops too and say, hey, what's the total electric field flux through this cylinder? And then we could correlate that total electric field flux to the amount of charge that's inside the cylinder. And what's that good for? It actually can be utilized in specific cases, or we should say highly symmetrical cases, to figure out what the actual electric field is due to the charge that's enclosed. So it's a nice thing to be able to extract out some notion of what the electric field is. But Gauss's law, very nice statement. In practical use, it's really only useful for really symmetric types of cases, certain charge distributions. The law holds for really all closed surfaces and charges enclosed, but some are really, really difficult to show. And there's other methods of determining electric fields as we've already investigated, right? But let's just look at one. Consider a point charge. I'm gonna change colors here. Black's running out. Consider a point charge. We'll just call it Q. And let's say, I'm getting ahead of myself a little bit, we'll consider that point charge Q. Sure. This nice little point charge Q there. And we are going to take this point charge and we're going to go ahead and surround it by, well, some sort of surface, which we're going to call Gaussian surface. The Gaussian surface is a closed surface that, well, encapsulates some charge configuration, some charge distribution, or in this case, a singular point charge. So the trick with Gaussian surfaces is to pick the right surface such that we can easily determine the flux through that surface. Because once we can determine the flux through the surface, we can say that that's proportional to the amount of charge enclosed. And there's a nice, easy constant of proportionality. So if there's a mathematical representation of Gauss's law, we'll get to in a second, and then we'll kind of compare things. But let's just think, what sort of surface can we enclose a point charge with such that the electric field flux through that closed surface would be really easy to calculate? What do we need? Well, in picking a Gaussian surface, which is again the surface that encloses, surface which encloses charge being considered. Picking a Gaussian surface, we look to achieve two things. Number one, that the electric field has a constant magnitude over the entire surface. Let's say has the same magnitude we need a surface that encloses such that the magnitude of the electric field is the same everywhere. So that's number one. And then number two is that there's a little extra here. Or say, or the E hat field is 0, because we can have composite surfaces like a cylinder, the top of the cylinder, the bottom of the cylinder, and then the cylindrical shell. Anyways, that's just a little extra tidbit there. Number two is that there is the same orientation with respect to the electric field and the area vector across the surface. Say the orientation of E hat with respect to A hat is the same everywhere. Regarding the surface. So, those are the two things that make utilizing Gauss's law doable. If you can't satisfy those two things, then Gauss's law probably going to be very difficult to apply to a system. Not impossible, but just more difficult. But this is what we want to do. Number one, what sort of surface could we have such that the electric field's magnitude is the same everywhere? Well, we know something about a point charge, right? A point charge has a radially outward or inward positive outward, radially outward directed magnetic electric field, that varies as 1 over r squared. Further you are away from it, the weaker the electric field is. So as long as we're the same distance away from this charge, the electric field magnitudes has to be the same. So as long as we're some, say, radial distance away from it, let's say some radial distance away from it, r, it doesn't matter if we're here, if we're here, if we're here, if we're here, out in front of it by that same distance, over here by that same distance. As long as we're 1 distance away from it, everywhere, we have ourselves that the magnitude would be equal everywhere, would be the same everywhere. So that kind of already confines us to one particular type of surface, right? What would that surface be? It would be a spherical shell. That's right. We'd have to surround this by a spherical shell where this charge is at the center of that shell, such that the shell's surface is the same distance away from the charge everywhere. So let's just go ahead and say, okay, well, let's think about a shell here. Say spherical shell is our Gaussian surface. And then we'll see about the other criteria. The other criteria is that the orientation of the electric field with respect to the area vector is the same everywhere. So what does the electric field look like due to a point charge? We already said it's radially outward, right? If the charge is positive, this is something that we already know. So in terms of the electric field, just drawing some electric field lines. Look at that. Drawing another there. Well, is that electric field going through that Gaussian surface in the same orientation everywhere with respect to the surface? And the answer is, yeah, look at this. This is like the normal vector with respect to this Gaussian surface, and it's aligned. It's aligned with the electric field. So that kind of falls out of what was necessary to make this first thing happen for this particular charge distribution. Hey, spherical shell is going to work out pretty good. The electric field is always radial, which is 90 degrees with respect to the tangent associated with the surface itself. All right, so, yeah, that's great. Okay, that one surface satisfies both of our criteria. So what can we do with this now? Well, first off, we can go ahead now and say that A hat is equal to A n hat. That's great. And then we have E hat is equal to E times R hat. That's great too. We have the area of the surface under consideration. We have the magnitude of the electric field. The electric field's radially outward, and this normal vector actually is radially outward as well. So n hat here is equal to R hat. They're in the same direction. So what do we have with this? Well, we can rewrite this. A hat is being equal to A R hat. Fantastic. Fantastic. Well, what can we do with the flux then? Well, let's just go to the standard fundamental aspect of flux. I'll change pens here again. We have the electric field flux. I should say net electric field flux, total electric field flux through the closed surface is the integral over a closed surface. I don't know if you've seen that little thing before there, but that means over the closed surface. So this is a surface integral over a closed surface of E hat dot dA hat. Which, because we have the nice preserved orientation, we can write this as over the surface. We can write this as being equal to the integral over the surface of E dA times the cosine theta. And then we say, well, is theta varying? Theta is the angle between the area vector and the electric field vector at all positions through space. They're aligned with each other at all positions through space. It's preserved. And furthermore, we've got ourselves, ultimately, theta is equal to 0 degrees at all locations. What's the cosine of 0? Cosine of 0 is just equal to 1. So now we've got this being that the net flux and electric field flux through the closed surface is the integral of E dA, and this again is over the surface. Well, there's something else that we did. We said that the electric field is going to have the same magnitude everywhere. So E is a constant. Oh, the magnitude's the same everywhere. So we can pull it out. There's no variance of the magnitude across the surface here. So this ends up being E times the integral over the closed surface of dA. Well, what is this right here? Hey, that's the surface area of a sphere. That's our surface. It's a spherical shell. What's the surface area? It's something that if you don't know, you could look up, or you just know it, and we've got ourselves at the integral of dA is equal to 4 pi r squared. Depends on your radial distance away from it, but we're just saying, hey, we're some radial distance away from it, r. So there it is. So what do we get out of this? Well, we've got ourselves then the net flux and the electric field flux through the surface is going to be E times 4 pi r squared. Fantastic. Look at that. There is the total electric field flux through our closed surface that is a spherical shell that exists at a radial distance r away from our charge. So what can we do with this? Well, this is where Gauss's law comes into play in terms of the expression for it. So we've got that for the net flux, and then we go back to Gauss's law and say, what does Gauss's law say to begin with? It said that the net electric field flux through a closed surface is proportional to the amount of charge enclosed. Proportional to it. How much charge is enclosed in this case? Well, the charge enclosed is just Q. There's also some constant of proportionality. Well, what is that constant of proportionality? That is something that we asked Gauss about, and we say, Gauss's law. Gauss's law ultimately says this: the net electric field flux through a closed surface, it's implied here, is equal to Q enclosed divided by epsilon naught, or epsilon 0. So that's the amount of charge enclosed right there. In our case, will just be that little q. And then we've got this. This is the constant of proportionality. Epsilon 0 is known as permittivity of free space. Permittivity free space. It is a universal fundamental constant. Permittivity. What is it? Well, epsilon 0 has a value of approximately 8.854 times 10 to the negative 12 coulombs per Newton meter squared. Messing up the units there. No, that's good. So this is the value. I was just questioning whether I had those units right. But yeah, has to work out to be flux, right? Flux is Newton meters squared. This would be coulombs. Divided by coulombs gives us meters squared. We're good there. All right, so what do we got? Let's put this all together. Well, this is our total electric field flux through our closed surface being a spherical shell. And what do we get out of it? We get that the total electric field flux is the magnitude of the electric field times 4 pi times r squared. So with this, and Gauss's law, via Gauss, we have ourselves that E times 4 pi r squared must be equal to Q enclosed. Q enclosed is just our little q here. So we'll have Q divided by permittivity of free space. All right, what can we do with this? Well, with this, we can now solve this for the electric field. Solve for E. Well, what do? We say that the electric field is equal to Q divided by 4 pi epsilon 0 r squared. What is this? That is the magnitude of the electric field due to the point charge. This is what Gauss's law is good for. It's good for determining what the magnitude of the electric field is. But it requires that you know some stuff about it, how the electric field behaves in general for a certain configuration. If you have no idea what the electric field is going to look like, how are you going to make a surface, right? A surface over which the electric field is uniformly directed and has a constant magnitude. You're not, if you don't know what the electric field looks like. So some of it comes with intuition, comes with some foreknowledge. In this case, yeah, we already knew what the electric field looks like. And we actually already knew what the magnitude of the electric field is. And it didn't look like this, did it? Huh, didn't look like this. We said that the magnitude of the electric field due to a point charge was K sub E Q over R squared. And now we're saying that the magnitude of the electric field due to a point charge is Q divided by the quantity of 4 pi epsilon 0 r squared. Shoot, did we mess something up? We're getting two different results, and the answer is nope, we're not messing anything up. They're the same results. K sub E, Coulomb's constant, is correlated directly with the permittivity of free space. This is the more fundamental constant. Coulomb's constant is an incorporation of this value. So, something to note here, we're going to see this epsilon 0 all over the place. And we just note that it's related to Coulomb's constant by a nice little factor here. K sub E is equal to 1 divided by 4 pi epsilon 0. Note that. There we go. So ultimately, we can also still write 1 over 4 pi epsilon 0. Hey, that's equal to K sub E. And we got ourselves K sub E Q over R squared. Which is then the same as Q divided by 4 pi epsilon 0 R squared. Check. Fantastic. That's it. We figured out what the magnitude of the electric field due to a point charge is by looking at the point charge itself that we already knew. Wow. Pretty neat, right? Well, this was just kind of to show the application of Gauss's law in a simplistic case that we already knew the end result. We're going to use it in a couple other cases, one that we already know the result, but to see how much easier it can make things, and then another case to extract something interesting out of it. So let me erase this stuff up and come back. Yeah, we'll do that. So be right back. All right, so what we want to do is look at something else that we've done but kind of see how the application of Gauss's law can greatly reduce the amount of work that's necessary. But again, the contingency is that we have nice symmetry arguments that we could work out. So, we'll say Gauss's law and the electric field due to a long straight line charge. With a uniform line charge density lambda. So we did this before, and we did it by integrating over the charge distribution relative to positions in space. But what we want to do with this particular case is not look at a segment. We can consider it to be long, so we're going to kind of use the infinite approximation here, which is necessary in order to make some sort of conclusions utilizing Gauss's law. So we take ourselves an infinitely long line charge with a uniform line charge density lambda. Say long straight, and we'll get to that. And this is a line charge density lambda, uniform. So what do we know about what the electric field looks like due to a line charge? What could we expect if it's infinite in length? And these are some things that we've discussed when we actually developed the expression for a segment, but there's some symmetry, there's some nice things. If we stick above this, in the plane directly above this line charge, what direction does the electric field have to be? Everywhere above it. And the answer is, well, if it's a positive line charge, it would have to be completely upward. Why? Because contributions from the sides would have equal and opposite x components, which would just leave us with the y components. That's it. What happens if we're below it? What about the direction of the electric field then? Well, again, from any points here, doesn't matter where, because again, this is infinitely long, we'd have equal contributions from the sides that would cancel out in terms of the x components, which would leave us with a negative j hat component, or a downward electric field. What about if we're projected directly out in front of this? Well, the components going out this way would cancel each other out, and we'd be left with an electric field pointing directly outward. If we're behind it, it'd be directly inward. Ultimately, if we take a little view of this where we've rotated it, and say that this is our charge that is basically line charge that keeps on coming out of the board, keeps on going into the board and out of the board, infinite, and we just kind of look at what the electric field looks like at this one location. The electric field looks like this, right? In this two-dimensional view, it resembles that of a point charge, but we'd have to remember that hey, this continues to go this way, so the electric field doesn't have components that wrap around in this direction. They're always pointing perpendicular to the direction that the line is pointing itself. So this is what we'd have for how the electric field behaves for a uniform line charge density lambda of an infinitely long straight line charge. All right, so then comes the question, well, should it stand to reason that if we're the same distance away from this line charge, above it, below it, in front of it, out to the side of it, if we're the same distance away, should the electric field be the same magnitude? And the answer to that is, well, yeah, because we're going to have the same combination of components, we're going to have the same distances away from all of the light components or all of the segments that have the equal contributions. Some cancels out, some add together, all in the same way, as long as we're the same distance away. So we've got two things going on. If we're a radial distance r away from this, whether we're above it or below it, or out in front of it, we have the same magnitude electric field. The magnitude of E hat at a radial distance it's constant. That's good. So that's something we kind of argue out and say, yeah, that has to really be the case for this particular type of distribution here. So that's good. That actually fits criteria number 1 for utilizing Gauss's law and figuring out some Gaussian surface. So then the other one is, what about the direction? Well, again, if I rotate this way, we have sort of a circular cross-section, right? Where the electric field would be perpendicular to that circular cross-section everywhere. So what does that mean? Well, it means that we could pick a nice surface through which the electric field, again, should be pointing upward, have the same magnitude above and below, like that, and outward and beyond. Pick a surface through which the electric field magnitude and direction is preserved across that surface. And we've got to think about it a little bit, but if you think long enough, hopefully you come to the conclusion that that surface would be some sort of cylinder, like a soup can. Take a nice soup can and we put the line charge through the center of that soup can, and we say the outer edges of the soup can itself constitute the Gaussian surface. Like a can, that's right. So across this can, we should have the same magnitude of the electric field everywhere, and the orientation of, I said magnetic again, the same magnitude of the electric field, and the orientation of the electric field would be this. So we just have something like this. We have the same thing as the point charge, right? We have the radial vector and the electric field vector and the area vector are all the same. So we've got kind of an A hat, we've got an E hat is the purple, and thus we have that E hat is equal to E R hat. This is cylindrically radial now, and A hat is equal to A times R hat as well. So when we go ahead and have ourselves this E hat dot dA hat portion, this resolves into E dA times the cosine of theta, where theta is equal to 0 degrees. Thus this E hat dot dA hat is equal just to E dA. That's over this surface. So this actually breaks into 3 different surfaces. So that's where you got to be a little bit careful. So that would be this surface. And let's just call this surface number 1, the cylindrical shell surface. But we've also got to close this charge that's contained in here. So we're going to say that this can has some length L, has a radius R, has a length L. Great. Well, we've also got to close off everything, so we've got this surface too. Let's call this surface number 2, and we've got this surface as well. Surface number 3. So this would be for surface number 1. What about surface number 2 and surface number 3? Well, what do we have? Well, across this surface, the magnitude of the electric field is going to be different, right? Different at different locations because we're different distances away from this point here. So R goes from 0 to R, basically. Ooh, is that a big problem? It's not. Because what do we have with the direction of the electric field versus the direction of the surface here? A hat's out like that. A hat's out like that on that side. A hat's perpendicular to the direction of E hat. If we've got A hat like that and E hat like that, this is 90 degrees. Or if A hat's like that, that is 90 degrees. And it doesn't matter if E was down or out of the board, as long as it's like this, it's always going to be at 90 degrees or perpendicular to the vector A hat. Thus, when we do E hat dot A hat for number 1 and, excuse me, number 2 and number 3, those surfaces, that's going to have to be equal to 0 because the cosine of 90 degrees is equal to 0. So there is no flux through these corners here. The electric field's completely radially outward. Nothing goes through this way. There is no component. Everything is this way, this way, this way, this way, that way, that way, that way, on both sides. So no flux through the end caps. So this is the only flux that we need to consider here, is through that cylindrical shell portion that we've got going on. So what can we do with this now? Now utilize Gauss's law. By Gauss. Oh my Gauss. We've got ourselves the net electric field flux through that closed surface is equal to the integral over the closed surface of E hat dot dA hat. Again, that's just general there. And this has to be equal to Q enclosed divided by epsilon 0. Q enclosed divided by epsilon 0. This is the net flux right here, and this is Q enclosed divided by the constant proportionality permittivity of free space. So this right here, again, this just reduces down into the integral now of EdA, because E dot dA just goes down to this. We have a constant magnitude and a preserved directionality between the electric field and the area vector. So now we have this, that the net electric field flux is going to be equal to the integral of E dA, and again, E is going to be constant over that surface, so we can pull it out. There's no variance of it. This again is still a closed surface. Let me be a little bit more specific here. dA1. Why 1? Because we've got a dA2 and a dA3 that are those end caps that have no contribution whatsoever. So this kind of resolves down into this. This is the only surface that we need to consider. And what have we got with that? Well, what is the area of a cylindrical shell? Disregarding the end caps of it. Well, we just have a circular cross section and then a length L, right? So what do we have? Well, we've got ourselves this area right here and then this length right here. Not area, excuse me. This circular cross section right here, and then it extends out some length L. So what do we have? Well, we want the circumference of the circle, right? The circumference here, extended out here, projected out, gives us the total area. So we've got ourselves 2 pi r times L. That is integral dA. All right, so what does this give us? Well, this ends up giving us E times 2 pi r L. So there's the net flux through the surface. What do we do then? Well, we compare it to the charge that's enclosed divided by permittivity of free space. So with that, we've got ourselves E times 2 pi r times L is equal to Q enclosed, sometimes just write ENC, Q enclosed divided by epsilon 0. Or Q sub IN, QN, there's lots of different subscripts that you may see. Anyways, this is what we've got. So the ultimate goal here, again, is to figure out what the magnitude of the electric field is. We've already got an idea of the direction, cylindrically, radially outward. So we solve this out for E, and we've got the E is equal to Q enclosed divided by 2 pi RL, epsilon 0. Q enclosed divided by 2 pi RL, epsilon 0. All right, so that's good, but we're not done yet, right? What do we need? We need Q enclosed. How much charge is enclosed? Do we know? And the answer is, well, it depends. It depends on the length of the cylinder that we chose. And it depends on the linear charge or line charge density. So how do we get Q enclosed? Well, lambda itself, lambda for a uniform line charge density is defined as the amount of charge, total charge, divided by the total length. The length's infinite. So the total charge over the infinite length of it would be infinity. But we don't need the total length. We just need to know what's enclosed. So we could also write that lambda, segment this out, is going to be equal to Q enclosed divided by the length of the segment that's enclosed, which is L. So what do we get out of that? Well, we get the Q enclosed as lambda times L. The amount of charge enclosed is equal to the line charge density times the length of the line that is enclosed. Boom, that makes pretty good sense, right? So what do? We put that up there. We're going to get ourselves that the electric field magnitude is then equal to lambda times L divided by 2 pi r L epsilon 0. Good, the L's cancel out. And we've got that this is equal to lambda over 2 pi r epsilon 0. Well, if you recall, what did we get for the electric field due to an infinite line charge? Before, we found E hat for infinite line charge is given by 2 k sub e lambda over r squared. We may have written a squared. A is just the distance away, r is the distance away. I prefer r, but it doesn't really matter. So this is what we had. And this again was a magnitude. Well, is this and this the same thing? That's not squared, sorry. 2k sub e lambda over r. And the answer is, yeah, they're the same thing. Why? Because k sub e is equal to 1 over 4 pi epsilon 0. We stick that in for k sub e, and what do we get? Well, we get this right here. That's it. Check, check. Something that we already knew, but if you remember what we had to go through in order to figure out what this was for the infinite line charge, we had to take the segment, look above the midpoint, and then go ahead and look at an infinite approximation. This ends up being a lot easier. But generally, Gauss's law and the application of it is difficult at first for a lot of people to sort of utilize and come to terms with. What am I doing? Area. There's a lot of little intricacies with it. You have to have some notion of the electric field, yeah, and you have to be able to determine what a Gaussian surface, what Gaussian surface can be used to satisfy the 2 criteria that make Gauss's law usable. Yeah, that can be a little bit more difficult than just trying to set up some integral, but the integral itself, that wasn't super easy to set up. We had lots of different variations with respect to determining this quantity here from the line segment. But it's just another method. And again, it comes in really handy for very symmetric cases in which you can find a nice Gaussian surface. But that's it for that part there. So we got one more nice thing to do with Gauss's law, and that is going to be something else that we utilize quite a bit in this course to get the idea of a certain aspect of an electric field. So again, I'll erase this stuff out, be right back, and we'll finish this up. All right, be back.